We have a quiz tomorrow on Biochem, right?
Yes, about the Krebs cycle.
Shall we study it together then?
That would be nice.
So we all know that Krebs cycle or citric acid cycle or tricarboxylic acid cycle is one of the very important reaction sequences in biochemistry. This reaction is responsible for most of the energy needs in organisms.
It is biochemical pathway that is used to generate energy to the oxidation of acetyl-CoA. It is also used for the synthesis of NADH and for the production of amino acid Krebs cycle. It takes place in the mitochondria of eukaryotes and the cytosol of prokaryotes.
But before we start the Krebs cycle, we should know about the pre-Krebs cycle.
We need to put glucose in it, which is a 6-carbon compound. It will then break down glucose into 2 molecules of pyruvate, a 3-carbon compound. This process is also known as glycolysis.
A pyruvate molecule will then undergo oxidation, aided by the enzyme pyruvate dehydrogenase complex, to produce acetyl-CoA, which is needed to start the Krebs cycle. The oxidation of pyruvate will also convert NAD+ and will produce the compound NADH.
That's the end of the pre-Krebs cycle. Now we will start with the Krebs cycle.
By condensation, the acetyl-CoA combines with oxaloacetate, which is a 4-carbon compound, to form citrate, and hence the resulting molecule is a 6-carbon compound. This reaction is catalyzed by the enzyme citrate synthase.
The citrate is isomerized into isocitrate by the enzyme iconitase.
Next, the isocitrate is oxidized into alpha-ketoglutarate by the enzyme isocitrate dehydrogenase. And in this reaction, a molecule of NAD is reduced to NADH, and a molecule of carbon dioxide is generated by decarboxylation. Hence, the alpha-ketoglutarate is the 5-carbon compound, since 1 molecule of carbon is lost into carbon dioxide.
The alpha-ketoglutarate is converted into succinyl-CoA by the enzyme alpha-ketoglutarate dehydrogenase by oxidation, and in this reaction, a molecule of NAD is reduced to NADH, and a molecule of carbon dioxide is released. Hence, the succinyl-CoA is a 4-carbon compound by decarboxylation.
This succinyl-CoA is converted into succinate by the enzyme succinyl-CoA synthase. In this reaction, a molecule of GTP, or guanosine triphosphate, is generated.
Succinate is converted into fumarate by the enzyme succinate dehydrogenase. In this reaction, a molecule of QH2, or ubiquinol, is generated, which is used for the production of flavin adenine dinucleotide, or commonly known as your FADH2.
Fumarate is then converted into malate by the enzyme fumarase, and
Last step, the malate is converted into oxaloacetate by the enzyme malate dehydrogenase, and in this reaction, a molecule of NAD is reduced to NADH. With this, the cycle continues when the acetyl-CoA combines with oxaloacetate again.
Now, let's look at the results of the pre-Krebs cycle and the Krebs cycle. Look, I have created a table for that one.
In the pre-Krebs cycle, 4-NADH, or your nicotinamide adenine dinucleotide, and 2 adenosine triphosphates, or ATPs, are produced.
in the Krebs cycle, 3 NADH, 1 FADH, and 1 ATP is produced.
In a cycle, only 1 pyruvate is involved, and since there are 2 pyruvate molecules, we multiply these numbers to 2. That makes it 6 NADH, 2 FADH, and 2 ATPs.
So there are 10 NADH, 2 FADH, and 4 ATPs in total.
We know now that there are 38 ATPs produced in total. So, how do we convert NADH and FADH to ATPs to be able to get 38 ATPs all in all?
We must take note that 1 NADH is equal to 3 ATPs and 1 FADH is equal to 2 ATPs.
Therefore, 10 NADH molecules multiplied to 3 is equal to 30 ATPs. 2 FADH multiplied to 2 is equal to 4 ATPs, and then there are 4 ATPs. The sum will then be 38 ATPs all in all.
Thank you for watching!